Hi everyone. So I'm gonna talk about a card game called Set. Talk about all the rules behind it and some nice like math behind it as well. I won't give you like nice proofs for everything, or even I can just give you some intuition, some of the pieces. Instead of giving you a talk about like kind of the stuff that I do, I thought this would be a little bit more fun. And still a way for us to like talk about math in different ways that we could see it popping up here. But my study or my field is in abstract algebra. Less broadly is in algebraic geometry, which is things with elliptic curves, which have some great applications that I don't study. I do a lot of like the theory behind it, but they are some complicated structures. And so they work really nicely with things like cryptography and stuff like that, like security wise. But yeah, there's like some pieces in here that look kind of like abstract algebra, and I'll talk in more detail about that. But if you are a pure math or some other of the majors, you will have to take like the proofs class, and then you'll have the option of doing the abstract algebra class, and you'll see a lot more in that class that has to do with this. In particular, I'll talk about things like modular arithmetic. A lot of my slides are already kind of set up, so I'm not going to be writing a bunch. So if it feels like I'm going too fast, please stop me at any point. If you have a question, please let me know. I will be asking you guys questions. So it'll tell me if you're paying attention or not. So just be mindful of that. And if you need me to go back on any of the slides, let me know and I can do that as well. All right, so we can get started. So this is going to be about the card game Set. Just a little bit of background on it. It was invented by Marcia Falco in 1974, so quite a while ago. She's not a mathematician, but it is very math. It's very on the math side here. She's a geneticist. And while she was studying epilepsy on German Shepherds, she was trying to find these specific patterns, which is how she got this idea for our set, our game Set. I don't know any other relationship between that. I don't know anything about epilepsy or genetics. So that's just the gist of what I know, how it came to be. But it did not come from a mathematician. It came from some other scientist looking for patterns here. Okay, so the first thing that we're going to do before we talk about the rules of the game, we're going to talk about what the cards look like. They're very specific characteristics and attributes within those characteristics. So we want to make sure that we feel comfortable with that part first, and then we'll talk about what the goal of the game is and how to actually play it. So the cards here are going to have shapes, and really it's going to be a number of those shapes in a color with a specific filling here. But usually we think of them going left to right. So the adjectives on the shape first. So how many, what the color is, the filling, and the shape. And so within these four characteristics, we're going to have three attributes that each card can have. And it's going to have exactly one of those in that characteristic. So here we could have the number 1, 2, or 3 for the number of shapes that are showing up. In terms of colors, we're going to have purple, red, and green show up. I know Dr. Ashley is colorblind, so I hope we can read this. Is anybody else having, okay. So in some of the pictures, I'm not going to say the color's not going to be written on it, but I'm happy to write it underneath to make sure that everybody can see what the cards are actually, what they actually have there. On the cards though themselves, they don't have the letters on here for the color. So if we end up playing, we can talk about it to see if there's some way around it. Also, is it too bright in here to see the color? Because I know with the black background it's kind of hard. Brandon, do you mind taking another light off? Is that hopefully better? Okay. Alrighty, so we have our numbers. We could have 1, 2, or 3 of our shapes. The color for the shape could be purple, red, or green. And in terms of the filling, it could either be striped, it could be filled in completely, or it can be empty with the color that you have here. So it could be striped, filled in or empty. And I'm just gonna show you like on a box what that would look like, right? We want stripes here, filled in. It's gonna be fully filled in whatever color you have. And then for the empty one, right, we'll still have the shape, but nothing will be on the inside. So that's what we mean by our filling here. The shapes, I'm gonna tell you what they are, but I won't draw them, but we'll see some examples so that we're okay with these. This is half the reason why I have most of my slides already ready, just to make it clear what the shapes are here. So we're gonna have things that look like an oval, diamonds, and then what we call a squiggle. It doesn't have like a nice geometric shape, but it's the most curvy one there. So we're gonna call it a squiggle here. So the first thing we're gonna do is just look at some cards and make sure that we understand what the characteristics are and what attribute we have between each one of those characteristics. Okay, so here are just 4 examples of what these cards could look like. On this first one, we have 3 shapes showing up. So the number attributed to this one is going to be 3. In terms of color, this is green. This is fully filled in, so I'll call it filled. And then this is a diamond shape. Okay, for our next example, this is the shape that I mean by squiggle. There's 1 red. This is going to be an empty squiggle. Again, for the empty ones, we see the shape, but the filling has nothing inside of it. Our third one here, we have 2 green striped squiggles again. Okay, and can you guys tell me the attributes for this last one? 2 purple striped. And I guess we didn't say the shape yet, but this is going to be our oval, right? It's not exactly an oval, but that's the closest thing that we do have to it because the sides are straight here. Okay. Any questions on the characteristics here? Right, again, we have 4 characteristics: number, color, filling, and shape. And within all 4 of those, we have 3 options for the attributes in that characteristic, right? So 1, 2, 3. Color, we have green, red, purple. Filling, we have empty, striped, or filled. And then the last is the shape, the diamond, squiggle, or the oval. Okay, so certain things that we can talk about, right? Actually, first, I'll say this. All the cards are going to be completely determined by these characteristics. They won't have anything else included in them or nothing less. Right, so it has to have all 4 characteristics showing up, and exactly one of the attributes will be showing up here. So it's not going to be half full and then striped at the bottom. It's either going to be fully filled, or it's going to be striped, or it'll be empty there. So as soon as we know what all the 4 attributes we have within those characteristics, we know exactly what card we're working with. Right, so it's uniquely determined by those 4 characteristics that we're working with. Okay, so if all the cards are unique in our deck, we can think about how many total cards we can have here. So really, what are all the possible combinations that we can have between these characteristics here? And so I'll let you guys think for a second to try to figure out how many cards we would have here if we're allowed to have all the combinations, and no 2 cards are going to be exactly the same. They're going to be unique to each other. All right, heard a couple people here. So what are we thinking? Anybody want to volunteer an answer?
3 to the 4th, probably.
Okay, and then how did you find that? Why did you use 3 to the 4th?
So you got 4 different categories.
We have number, we have color, filling, and shape.
And then there's 3 possibilities.
right? And really, they don't depend on each other. If I choose one for my number, it has nothing to do with the color that I choose. So they're completely independent choices that we're making, which is why we can just multiply all these numbers together to give us the full combinations here. Right, and so if we multiply these together, we'll get 3 to the 4th or 81 cards. So in a deck of in our deck of set, we're gonna have exactly 81 cards in here. So one for every single possibility that you have. And again, they're all gonna be unique. There's not gonna be any repetitions in the cards here. Okay, any questions on how we figured this out, this number here? Okay, so our goal right now is to find as many sets as we can possible. Really what we're gonna do is we're gonna put 9 cards down on a board, really on some platform, and we're gonna search for sets. And as soon as you see one, you're gonna pick it up and we'll replace those cards once we're done with that. But we need to know what a set is first before we can think about finding the sets. So we'll talk about the definition of what a set is in this case. So I'm always gonna call it, or write capital SET, so that we don't confuse it with a collection of objects, which is what we think a set is mathematically. Okay, so our set here is gonna be a collection of 3 distinct cards, where within each individual characteristic, all 3 cards either have the same attribute or they all have the different attribute there. So if I think color, they're either all gonna be the same color, so they can be all red, or within the 3 cards, they all have to be different color. So one has to be red, one has to be green, and one has to be purple. And just because it's all the same in the color doesn't mean it has to be all the same in a different characteristic, right? They're gonna be independent of each other. But within each individual characteristic, they're either all the same or they're all gonna be different. So we'll look at some examples of 3 cards and we'll try to decide, does it give us a set? Does it not give us a set? And if it doesn't give us a set, we wanna talk about why it doesn't. So really this is gonna end up being some pattern recognition when you actually play the game. Is figuring out what types of sets are easier for you to find, what type of attributes are easier for you to see. But really, excuse me, the more practice that you have playing the game, the easier it'll be for you to find these patterns. And I've learned that playing with people that are more experienced is actually super helpful because they'll find sets that you weren't able to find. So it's definitely a good way to learn how to play. Okay, so let's look at some collection of 3 cards, right? Because the first thing we need is 3 cards where within each characteristic, they either have the same attribute or different attribute. So we're just gonna look at the first set 3 here. Okay, in this first card, we have 2 purple diamonds that are striped. And then we have 1 red filled in squiggle, and we have 3 green empty ovals. Okay, so we can think through these together just because this is still pretty new. So let's just go one characteristic at a time. Decide, are they all the same in that characteristic or all different? And if it's neither, then we know that it's not going to give us a set. As soon as it's neither in one of the characteristics, we know it's not going to give us a set back. Okay, so here, let's think color. And what do we see about the color? Yep, they're all different. So in terms of color, we're good here. Okay, next up, we can look at number. And here, what do we have? All different again. We have 1, 2, and 3. And in color, we had purple, red, and green show up. Okay, we also have filling that we need to check. All different again. We have empty, striped, and filled. Okay, and the last thing is our shape. And again, all different shapes. We have diamond, squiggle, and oval. So this is a type of set where all the characteristics are all different. Personally, these are the hardest for me to find, or when all the characteristics are different here. I like having some similarity there because it's easier for my eyes to draw to those. Something else to note is that we can't have all of the characteristics all be the same, because then we wouldn't have 3 distinct cards showing up, right? Because as soon as they're all the same, they're the exact same cards showing up. And our set here, or our deck, all the cards are going to be unique. We don't have any repetitions of our cards. So we can't have all the same, but we can have all different characteristics here. Okay. And just by looking at it, before we like dive in on the specific attributes, what do we think about this second one? Is this a set or not a set? Anybody else? Or you want to raise your hand if you think set?
Is the middle one striped?
The middle one is striped, and I can zoom in. Hopefully that's easier to see. And we have green, red, green, for those who can't see the color, which that alone should give away the answer to it. Okay, so people who think that this is not a set, can you tell me why you think it's not a set? Yeah. Right, here we have an example where we have green, red, and green again, right? So in that characteristic, we're seeing that we don't have all the same color or all different color. It's somewhere in the middle, and so that's not going to be included as a set here. So just by the color alone, we can see that it's not a set. Possibly there's other characteristics where it also breaks being a set, but as soon as you see that one of them is not all the same or not all different, you can say it's not a set and you can move on, right? So here we can see in terms of color, they're not all the same, and they're not all different. Okay, is there another attribute here that would tell us that it's not a set? Right, the shape again, we're seeing 2 of the same shape, but the third one is a different one. So in terms of shape, again, it's not all the same and not all different. So as soon as you see just one of them is different in that characteristic, or exactly one of them is different in that characteristic, you can say that it's not going to be a set here. Yep, and even the number, right? We're seeing 212 show up. So it's not all the same number or different number. It's not 123 or all like 222, 111, 333. Okay, so this last one here was examples, just to get some good practice here. Okay, and let's focus in on this first one, where we have purple, red, and green, and that middle one is striped, just in case it's not easy to see. So just off the bat, what do we think? Set or not set? Okay, so more leaning towards set, but to actually check, we'll look at all the characteristics. So we'll start off with number. They're all 1s, right? So they're all the same. In terms of color, they're all different, right? Purple, red, and green do show up here exactly once. In terms of our filling, they all are different here. One is empty, one is striped, one is filled. And then in terms of the shape, these are all different as well. So here we have an example where in one of the characteristics, all the attributes were the same, and then the rest of the characteristics, all the attributes were different. So we can have different variations of that showing up. But again, the only thing that can't happen is that they're all going to be exactly the same in those characteristics. Okay, so this does give us an example of a set. Okay, and let's look at this one here. Again, we have the colors red, purple, and green here, and all of these should look like stripes. Hopefully you can see the stripes on your side. And what do we think? Not a set, right? As soon as we see two diamonds and one different shape, right? So it could have been a squiggle or an oval. We can see that this is not going to give us a set because within the characteristic of the shape, we don't have all the same and we don't have all different here, right? So as soon as you find one characteristic where it doesn't follow the rules or the definition of our set, then we're good. But to actually show that it's a set, we do have to look through all four characteristics and make sure that it does follow the definition there. Right, so this is going to be not a set. And one of the reasons here is going to be for shape. So they're not all the same and not all different. Right, and again, the only way that that could really happen is if we have two the same and then the third one is a different. It doesn't matter which different one it is, but it's something else from those two attributes that you see. Okay. Any questions on the examples that we had? If you want to look at the explanations again together, I'm happy to do that. But understanding what is a set is going to be really important. So we want to make sure that we have a decent understanding of this here. Okay, so we're gonna think through some questions together. So if I give you one card, do I know that there's a unique set that it's going to be a part of? And then my second question is going to be slightly different. If I give you two cards, do I know that it's a part of one unique set here? Or do we have options? If I give you one card, do I know it can be part of multiple sets? Or if I give you two cards that I want to stick together, can they be a part of more than one set here? So let's think about the first one. And what do we think about this? If I only give you one card, is there only one unique set it can be a part of? Or are there multiples for this here? Multiples. And really, no matter which card I give you, there really are multiple sets that they can be a part of. And it turns out for every single set or for every single card, there are 40 sets that it's going to be a part of, 40 unique sets that they're going to be a part of. And that shouldn't be obvious to you right now. But there really are multiple ones. There's not one unique set that it can be a part of. So here, we're going to say no. There are actually 40. And I don't think I had an example earlier within my two. Nope, I did not do that. Right, but you can pick one card, then decide for the second card that you want it to be a part of, the set. You can decide if you want the attribute to be the same or different. And then once you made that choice, this is actually going to answer the second problem. Once you decide what the second card is in your set, it'll completely determine what the set is. So as soon as you pick two cards, if you want to make a set with it, there's one unique set that they can be a part of, right? So here for the second one, the answer is yes, there's a unique set. So if you look at the individual characteristics, so if I work with, let's say, color between the two cards, they're either going to be the same or they're going to be different. And that'll determine what the third one has to be, because all three either have to be all same or all different. So if then both numbers were 1, then my third card had to have one shape in there. If one of them was 1 and 3, they're different. And so my last card has to be 2 so that we have all different numbers showing up. And we can do this with all of our characteristics. As soon as we have 2 cards here, it tells you if within that characteristic, the attributes will be all different or if they'll be all the same. And it'll tell you exactly what the third card would have to be there. Lots of times when people play set early on, this is kind of the technique that they use. They pick 2 cards in like the 9 that are on the board, and they try to find the unique third one that makes that a set. It's not likely that that card is going to be in that pile of 9. And so it's hard to do that because you really have to take all the pairings that you find. Right. What ends up happening is we start to see these patterns and it makes it a little bit easier to find them versus taking 2 at a time and trying to find that unique one. Right, but for this answer here, yes, it's going to be a part of a unique set here. So, right, within a characteristic, the two cards either have the same or different attribute, which completely determines the third card here, or the characteristic within that card. Ran out of space. And then you can do that for every single characteristic to tell you exactly what attribute that third card would be. And as soon as you decide what all 4 attributes are, it uniquely determines what the card is. Okay. Any questions on this explanation here? Right, and if you actually think about the second question first, it'll make it a little bit easier to think about the first question. If I pick one card at random and want to think about all the sets it can be a part of, I said I had 81 cards in total, but I can't choose itself to be in the set again. So I really only have 80 options for my second card. Yes, 80 options there. And then I can uniquely determine what the second card will be, right? But I said 40, and right now I said 80. It turns out there's going to be multiple that are the same, right? Because as soon as you pick the second one, it determines the third one. But I could have picked that third one first, and that would have determined the second card, right? So there's going to be pairings of 2 showing up that are exactly the same, but maybe in a different order, but they mean the same thing in the game. No matter how you pick up the 3 cards, it's really just the collection of those 3 with the specific attributes that make it a set. So you do actually end up getting 40 different sets for any one individual card that you pick. Okay. Great. So during a game, you'll place 9 cards on the board, and really there's no board that comes with it. You'll just put it like on a table or something. And you begin to search for sets. So you'll look for 3 cards that, right, again, within each characteristic, they either have all the same attribute or all different. And if you think you've seen one, you call out set and you pick up the 3 cards and you take them. And really the number of sets that you have at the end are the points that you get. So the more sets that you find, the more points that you'll get at the end. Right, and then we replace the 3 cards that we took away so that we still have 9 cards after we pick them up. And we want to be careful, right, especially when we're first starting out, that we're actually picking up sets or correct sets. So usually we'll take it a little bit slow at the beginning and kind of prove it to ourselves that we are actually picking up a set, that there was actually a set showing up there. Okay, so it turns out that if you have 9 cards on the board, you're not guaranteed to have a set on the board. If I pick any random 9 cards, the chances are not that high for you to be able to find a set there. But the more cards that we add, the harder it is for us to be able to see the patterns showing up or finding sets. So this is one reason we start with 9, to make it easier on our eyes to be able to find the patterns. But it turns out that you need at least 21 cards to guarantee that a set will show up. This doesn't mean that if I have less cards that I won't have a set show up, but it just might be less likely and just not guaranteed to happen. If I say I had 20 cards on the board, there is a chance that there is no set there. Right, but proving that to ourselves can be kind of hard, to show that there's no sets showing up. So really what we need to do is we all need to agree that there is no set before we want to add more cards. Because if there's no set there, right, we need to add cards to be able to find one. So as soon as we all agree that there are no sets, or if we're tired and we're just like, just add 3 more, then we'll add 3 more cards, and hopefully it'll make it easier for us to find a set. But we do want to think about how do we convince ourselves that there are no sets on the board. So we'll look at some examples of 9 cards where I've already I pick them strategically so that I know that there are no sets in the cards. But we'll talk about why can we say that. What about these 9 cards will help us determine that there are no sets in the on the board. Okay, so this is what like a first round would look like, right? We would place 9 cards on the table, and then we look within our characteristics to try to find some patterns here for our sets. One thing that we'll notice here is that we only see red and green showing up on the board, right? So what this is telling me is that I can't have a set here. If there's a set, I can't have a set here that has all different colors because I don't have a purple card, right? So what this is telling me is that I can think within just the reds, do I have any sets there? Because they have to be the same color. So they're either all going to be red or they're all going to be green here, right? So I can almost forget about that attribute and just look at the green cards, and within those decide, do I have any sets? It'll shrink the number that we're working with, so it'll make it a little bit easier for us to determine. And then the same thing within the red, look at all the red cards and then decide within just the red, do I have any sets showing up? Okay, so maybe let's look at the green first since we have less green cards. So the green cards are going to be these 4 here, just in case you can't tell the difference. Okay, and what can we say here? Can somebody give an explanation on why these don't give us a set? Yep, so within the shape here for the green ones, we're missing the oval. So they all have to be the same shape, but there's not even enough of the same shapes to have a set here. There's not 3 same shapes showing up within the greens. So we know automatically there are no sets within the green cards. Just by that. Something else we could tell was through number as well. Here we have 1s and 2s showing up, but no 3s. So that's telling me I have to have the same number within the greens. But again, I have 2 1s and 2 2s, so not enough to make a set again, right? So we can see that there are no green sets, but now we have to convince ourselves that there are no red sets as well. This is a little bit harder just because there's more cards showing up here. But looking at the number, this will help us, right? We can notice that there are no 1 red cards. There are only 2 and 3s. So for it to be a set, they would have to be all the same. So we can look at all the 2 reds on their own, decide do they give us a set, and then all the 3 reds by themselves and decide to do those give us a set here, or any combination of 3 cards. Again, we'll see with the red ones, we have 2 here that are 2, but there are no more, so I can't make a set with 2 cards. I do have 3 cards that are red, that have 3 shapes in them, but there's exactly 3, so we can determine is it a set or not. And here, just through the shape, we can see that it's not going to give us back a set because we have 2 squiggles and 1 diamond, right? So it's not all the same shape and not all different shape. So we see within the reds, we also don't get any sets here. It's really nice when one of the attributes does not show up. So the fact that we didn't have a purple made it really easy to kind of partition our cards into 2 different colors and work within those 2 to decide if we have sets or not. When we have all the attributes showing up, it makes it much trickier for us to convince ourselves that there are no sets there. And really a lot of keeping some of that stuff in your memory. What things did you already check? Okay, and let's look at one more example of a set of 9 cards that again does not give us back any sets here, or a collection of 9 cards. Okay, so notice here we do have all 3 colors showing up. So I'll put P for purple, and then R for red, and anything I didn't label would be green here, and I'm putting them underneath the card. Okay, so looking at the shape, or excuse me, the color, it's not going to be quite as easy to determine if we don't have any sets here because we have every color showing up. Okay, but is there another attribute that we can look at that maybe is not showing up or is showing up less often than the other ones are? The middle card? Is that what we said? Oh, the fill. Right, so if we look at the fill, so we want to look at empty, filled, and striped, we only have one striped card. Okay, so this is not quite as nice as our last example, where one of the attributes was completely missing. But this is the next nicest thing, where we have the attribute show up, but only one card has that attribute. So if there's going to be a set where all the fillings are different, this card has to be part of the set. So we can think about all the possible sets that this could be a part of with the cards showing up. And then we can also think about if they're all the same filling, what sets would show up there. So it gives us a few more partitions to kind of think about, a few different collections of cards to look together to decide. But this is not too bad to convince ourselves that there are no sets here. So if I look at my striped card here, if this is a part of a set, again, it has to be paired up with a solid and an empty. Notice that there's only 2 solid cards, so it's easy to check comparing with the solid cards to see if the third unique card in that set is going to show up. So we see that there is a filled in squiggle here. So if these two form a set together, what would the third card be? Empty, I believe empty, I believe purple, I don't believe diamond, oval, and then what about the number? Okay, so 2 open oval oval, that's not right. 2 open purple ovals. And do we see that show up here? Right, that card is not showing up here. So we can immediately see that that 3 diamond stripe that's showing up here cannot be matched up with the filled in red. So if there is a set here with that empty or with that striped diamond one that we're seeing, it would have to be with the other filled in one, this one here. And so we want to think about what set or what card would complete that set and does it show up here? So we have 2 filled in ovals and then 3 striped green diamonds. And so in terms of number, it would have to be 1. In terms of color, it would have to be green. In terms of filling, it would have to be empty. And in terms of shape, it's going to be a squiggle here. Right, so we said 1 empty green squiggle. 1 empty green squiggle. Do we see that show up on the board? No. So this is telling me there's no way that I can include this striped card here in my set. And since it's the only striped one, I would have to have all the same filling if there is a set showing up here. And that turns it into a problem that we worked with before. So we'll look at the same fillings. So look at filled in. We only have 2 of them, so not enough to make a set. And then we have 1, 2, 3, 4, 5, 6 empty ones. And within those, we need to decide, do we have any sets that we can make? Any 3 cards we can put together to give us a set here? And what do we think here? So it's not quite as straightforward. And why?
Because like the triangles, we don't have any triple triangles that are empty in a green color. Then we have to go with the squiggles. We don't have any single squiggles that are empty in a color.
Right, so we can think about shape here to help us determine, but we don't want to get too particular. We don't want to say, look at all the diamonds that are empty, because there are different ways that diamonds can be put together here. So we want to be a little bit more careful. So if we do look at the shapes, we don't see an oval show up in these empty cards that we're looking at. So they do have to be the same shape here to form a set. And here we do have 3 empty diamonds. We have this one, and this one, but they don't form a set, and there's only three of them. So I'm not gonna get a set with those cards. And so the only thing I have left are my squiggles, which are empty. The colors look good, but the number does not look good here. And so this is enough now to say that we don't have any sets within the empty ones. We don't have any within the solid ones. And since there's only one striped, we can say that there's no sets with all different shading there. Okay. Again, this does take quite some work to decide that there's no sets in here. But the more practice that you get, the easier it is for you to determine, or for you to have a good intuition that there are no sets left. Early on, we don't have to actually prove it to ourselves, so we can just add another card or two to help us hopefully find a set by adding those cards in there. One nice thing about knowing that there are no sets there is if I add one more card, if there's going to be a set, that card has to be a part of it, right? Because I already knew within the 9 that were up there were no sets. So determining that before you add a card makes it a little bit easier to find the next set that might show up there. Okay. Any questions on that? Okay, so I think I only have time to talk about one last thing here, which some people call the end game. There's actually like a book on the game of set with different types of things that you could do, like do some counting problems, you can do some modular arithmetic, you can think about geometry, and it answers a bunch of different questions within the game. But one of the things that I think is kind of neat is that there's a way to completely determine what the last card is during the game before flipping it over at the end. Of course, if you flip it over, you can determine what it is. But as long as you haven't made any mistakes, if we didn't pick up any 3 cards that were not sets, there's a way for us to see at the very end, before flipping the last one, we can determine what that card is exactly. We can determine what all of the 4 attributes will be in the characteristics, so we can determine uniquely what that card is there. We do have to do a little bit of work to try to understand the reasoning behind it, and so we'll do a little bit of that now. And this is where modular arithmetic is going to show up. And if you haven't heard of modular arithmetic, that's totally fine. I'll talk about it hopefully in a context that you understand first. And then really we're going to think in mod 3, because we're thinking about 3 cards and there's 3 attributes within each of the characteristics. Okay, so what we need to do is we need to talk about what modular arithmetic is, and then we'll decide through that how we're going to represent each card as a vector. So we're going to describe or represent each card as a vector with 4 entries, 1 entry for each characteristic, and we're going to give a value for every single attribute within that characteristic. And that's where our modular arithmetic is going to come into play. We can think about adding the vectors, and then mod 3, one thing is always going to be true if you're looking at a set. If you're looking at 3 cards that make a set here, but we'll go into more detail there. Okay, so first we need to think about modular arithmetic. Some people call this clock arithmetic because this is like the first example that we usually see, right? Either working with a 24-hour clock or with a 12-hour clock, but usually the 24-hour one works a little bit better because it tells you exactly what time of the day it is, versus a 12-hour, you need to determine if it's AM or PM, which makes it a little bit more vague there. So let's think of a question together and try to come up with the answer. So let's say, oh, I might have written this already. Yep. Let's say that it's 10 a.m. right now, which it's not. But let's say it's 10 a.m. and we want to determine what time it'll be in 5 hours. So what would we do to get to that answer of 3? How did you get to 3? Take 2 off of 5.
So 10 plus 5 is 15.
Yep. So we have 10 plus 5, which gives us 15. Really, we can think of 15 hours after midnight. That's how we think of 10 a.m. as 10 hours after midnight. And so we can think about what this 15 represents in our 12-hour clock. If we were thinking 24-hour clock, this would be our answer. But if we want to think in our 12-hour clock, I can subtract multiples of 12 until I get a number between 1 and 12 here, right? So here I can subtract off 12 to give me back 3. And really these are equal mod 12. So when we're thinking of a clock that just have 12 numbers on it, saying that it's 15 o'clock is the same as saying it's 3 o'clock. In this case, it's not as obvious what exact time of the day it is because mod 12 again does not tell you AM or PM. But we saw that it went past 12 here. And so that is going to give us a PM here. So this will represent 3 PM versus 3 AM. Okay, another way that we could think of this is we can do our 12 plus 5, which is 15, and then divide it by 12. So I can think about 15 divided by 12 because I'm thinking mod 12 or my clock having 12 hours. And really the information that I'll get out of this that I want is going to be my remainder. Really, when I think mod n, I want to think my remainder after dividing by n. In this case, if I want mod 12, I want to think about my remainder after dividing by 12. So I can do some long division here, put my 15 here, my 12 here, and I want to decide how many times does 12 go into 15? And it doesn't have to be exact, right? It goes in once and it doesn't go in twice, so I'm going to write 1 here. Multiply that by 12 and subtract to give me 3. I don't have any other placeholders showing up after my 15, so I don't have to bring anything down to then see what 12 goes into this new number. And really, I know I can stop because of that point and because what's left over here is less than 12. This is my remainder. So I can think of 1, remainder 3 as my answer. And so I should really be thinking mod 12. This is going to be 3 because this is my remainder after I've divided by 12. And I really want my answer to be between 0 and 12 to really understand what that means in terms of our clock. And when we're doing modular arithmetic, that's what we want to happen. Even if it's not 12 there, let's say if it was 3, I would want my answers to be between 0 and 2 versus bigger numbers there to say exactly what it is. Okay, the reason why these are the same, thinking about it as the remainder versus pulling out a multiple of 12 or subtracting by 12, really by subtracting the multiple of 12, we're thinking about how many times will 12 go into 15? That's why I subtracted that 12 once. And then what I get left over is going to be that remainder showing up there. So I could either think about it as my remainder after dividing by 12, or after subtracting or adding multiples of 12, seeing what number I have left over that's between 0 and 12 there. Right, so there's a couple ways that might make it easier for us to determine what the time is here. Right, but for our answer here, if it's 10 a.m. right now, in 5 hours, it's going to be 3 p.m. Okay, so let's also think in terms of a 24-hour clock, just to get a good grip on this here. So instead of thinking mod 12, I'm going to think mod 24. So it's okay if I have answers that look like 13 or 18 or 20, as long as they're less than 24, it gives me a good representation of what time it is during the day. Okay, so now let's say it's 2 o'clock, which it's at least closer to that time. And we want to determine what time it'll be in 100 hours. Okay, so any thought processes on how we want to determine what time it is? Mm-hmm.
If you think of 2 p.m. as 1400.
Yep, 2 p.m.
24-hour clock, and then you add 100 hours to it, 114 hours. You know that 114 closest visible is was 11/12, which gives you 121.
Okay, so You were saying about pulling out multiples of 24, right? Because we want to do the clock on 24 or mod 24 now, which is a little bit trickier if you're not good with quick multiplication here. But here, let's see. I want to think about how many 24s can I pull out of my 114. And I can do 24 by 4, which is 96 here. So I can write this as 96 plus 18. And this is the same as 4 by 24. Please check my arithmetic here. I did this before, but just in case. So here I'm seeing I can pull out 4 copies of 24, and I get left over 18, which is less than 24. So if I actually had done the long division, I would have seen that I would get, after doing 114 over 24, I would get remainder 18 here. So when I'm thinking 24, mod 24 or 24-hour clock, this is 114 hours later, is really saying 18 o'clock. And if we want, we can think in terms of a 12-hour clock, what that would mean. I can subtract a 12 off of here to get 6. And because this is 18, it tells me AM or PM. This is really telling me 6 PM. Okay. So we can also say how many days later that would be. It would be 4 days later at 6 PM, but we only asked for what specific time it was. So we can say that it's going to be 6 PM here. After thinking about how many multiples of 24 can I pull out and what my remainder would be left is exactly what it would be equivalent to mod 24. Okay, so again, this is the reason why some people call it clock arithmetic instead, because we're really doing some of these calculations throughout our day. But we can think about mod or modular arithmetic with more than just 12 or 24. We can pick any positive integer or a natural number here to think in terms of mod. And really the one that we want to stick with, and I'll move ahead a little bit, is we want to think in terms of mod 3. So modular 3 or mod 3, they really mean the same thing. So here, and again, the reason why 3 is the special number we want to work with is because we need 3 cards in our set, and we have 3 possible attributes within each characteristic. So the values that we're going to care about, mod 3, are going to be 0, 1, and 2. Just like mod 24, we really cared about 0, 1, all the way up to 23, because those are the possible remainders you can have after dividing by 3. If you get anything bigger, that's telling you you should have divided by more. So really 0, 1, or 2 are the values that we really care about, modular 3. And we can think about adding these numbers together and thinking modulo 3, what would that look like? Just like we did with our mod 12 and our mod 24. So if I did something like 0 plus 1 plus 2, that's literally going to give us 3. But if I want to think mod 3, so after dividing by 3, what would the remainder be? I think I heard a couple different answers. 0, right? If we divide by 3, we'll get 1 remainder 0 here. So this is equivalent to 0 mod 3. So if I add 0, 1, and 2, I really get back 0. And I really want all my answers to either be 0, 1, or 2 here. If I did 2 plus 1 plus 2, if I add those up, I'll get back 5. Which is what? Mod 3. 2 mod 3, right? Again, I can think of a remainder, or I can take away multiples of 3 until I have a number between 0 and 2 inclusive. And so we really want to feel comfortable just adding 0, 1s, and 2s and deciding what do we get back out, mod 3, because these are the values that we're going to give to the attributes within each characteristic that we have. This is really going to be the entries that show up in the vector that represents the cards that we're working with. Okay, so we're gonna represent each card as a vector with 4 entries. Again, the 4 entries are completely determined by the characteristics. So if I had a card here, I want the vector, again, to have 4 entries. The first one to represent the number, the second to represent the color, the third for the filling, and then the fourth for the shape, where I'm gonna give them specific values for each attribute in that characteristic so that it completely determines what the card is. So again, we have 3 options within all of these categories. And so this is why we're gonna think mod 3. So each attribute has 3 options. So we'll think mod 3. And I'm gonna give them all values either 0, 1, or 2 within each category or characteristic. Okay, so this is a similar table that we saw earlier, but now I have an extra column where I'll tell you exactly what the value is for that attribute. Since I wanna use 0, 1, and 2, I'm gonna have the numbers match up a little bit nicer here. So the value for 1 is gonna be 1, the value for 2 is gonna be 2, and because I wanna be 0, 1, or 2, the value for 3 is gonna be. And really, all our rows are gonna have the same value. So if it's 1, if it's purple, if it's striped, or if it's oval, it'll have 1 in the specific entry for that characteristic. And then for the second row, if it's 2 red, filled, or diamond, it'll have 2 in that specific entry. And then if it's 3 green or empty or squiggle, it'll have 0 as the value in the vector there. So we'll look at an example here, deciding what the attributes are, or excuse me, what the vectors are here. We'll notice this is first one is purple, red, and green. We'll notice that this does give us back a set, and we can think about adding our vectors. And something very specific is going to happen when we have 3 cards that form a set here. If we add up our vectors, we'll see that we're going to get the 0 vector, and we'll use this as an example to help us see that. So for this first one, we have 1 as the number of shapes showing up. So that value is 1. We can look up. This is going to be purple and empty. So for color, it's going to be 1 as well. Said it was empty. So for the filling, it's going to be 0. And then the last thing is the shape, which is squiggle, which is also a value of 0 that we determined or that we set at the beginning. You can set these to be anything that you want, and it should still work in a similar fashion here. And just so that we don't have to go back and forth, I can tell you what the second one is. It'll be 1, 2, 1, 1. And then this last one is 1, 0, 2, 2. Okay. And if I want to add vectors, there's one way I can do this, which is usually the canonical way to do it, is to look within each entry, really add by component wise. So if I look at the first component of all 3 of my vectors, I'm really going to add all those values together. So for my first entry of this sum, I'm going to have 1 plus 1 plus 1. And then later on, I'll reduce it, thinking mod 3. And I'm going to look at my second entries and add those together. 1 plus 2 plus 0. Look at my third ones, which is 0 plus 1 plus 2. And then the fourth ones, which are 0, 1, and 2 as well. Okay, notice here on the first one, this is where we were looking at the number. They were all the same. So I had 1 showing up in all of them, which is going to give me back 3, which is equivalent to what mod 3? To 0 mod 3. If I look at my second entry, that was representing, I believe, our color, or actually, yep, our color, which these are all different. So all the entries are going to be different here. So I'm really adding 0, 1, and 2 and some specific order. The order doesn't matter because adding those numbers in a different order will give you the same product. So here again, if I add 0, 1, and 2, I'll get back 3, which we already determined was 0. And the same thing is true in the other 2 components. I'm adding 0, 1, and 2 again, so I'll get 3 or 0 for that entry. This is a nice vector. This is what we would call a 0 vector. It works really nicely for us here. Just like the number 0 works really nicely with the real numbers. If I add it to any number, I'll get back that same number. Or if I do a number minus the 0, I'll get that number back out again. And the same thing is going to work here no matter what vectors I work with. If I add the 0 vector or subtract the 0 vector, I'll have the original vector that I started with. Okay. Right. So anytime that you have a set, if you represent it with your vectors here and add them up, you'll always get the 0 vector back out. The reason for this, again, is if they're all the same attribute, they're either all 1s, all 2s, or all 0s. And in all 3 of those cases, if you add them up, you'll get 0 mod 3. And in the case where they're all different, you're going to be adding 0, 1, and 2 in whatever order you want. And again, you'll always get 0 back out at the end. So again, for a set, if you add up the vectors representing them, you'll always get the 0 vector back out. So let's quickly make a connection between these vectors and how this will actually help you determine what the last card is. Oh, this was the question I already answered. It gives us back the 0 vector. Right, but what we can do here is we can look at a specific characteristic. So I can think of color, and just within the colors, I can forget all the other characteristics, all the other attributes. I can determine what my last card is if I try to make sets within just the colors. Right, and really what this comes down to is the fact that when you take away a set, you're really taking away the 0 vector out of the total that you have on the board. And taking away the 0 vector is not going to change the sum that you have of those vectors, right? So within each characteristic, the sum at the end has to be 0. And so by making these sets together, just looking at one characteristic at a time, one component at a time, you're making sure that 0 is in the entry of that component, right? So again, if you fix one characteristic, forget all the rest, try to come up with sets that show up there, it'll tell you exactly what the last card will have to be. So you can look at just one characteristic at a time. And make sets with just that characteristic in mind. And this will fully determine the last card that would have to show up. Again, this is dependent on us not making any mistakes prior, because as soon as we take away a set or 3 cards that don't give us back a set, this theory is not going to work here. There might be times where it will work out conveniently, but we're not going to be guaranteed that we can determine the last card if we've made a mistake on the way. Okay, and I'm going to skip a little bit of the explanation. I did give a little bit of it here, but let's just try to think about how do we actually determine this here. So if I give you any random 8 cards, it's not necessarily the last 8 cards of a game. So I did have to be pretty strategic on which ones I picked here. So this is assuming I did not make any mistakes prior. I can now determine exactly what this card has to be. So I can look one characteristic at a time. I can look at numbers. And so just looking at the cards as if just the number is showing up, I can start to make sets together, which is a little bit easier, either all the same or all different numbers. Here, I can group these 3 together, all ones. I can also group these 3 together because they're all 3s. And what I'm left with is here. this last card again has to make a set with whatever's remaining there. So this is telling me I have to have 2 objects in my card. So I'll have a 2 here just to help us remember. Okay, if I think about my color, and just my color, I can determine what the color of the card is. So here I'm gonna group things that have the same color or 3 that are all different. So I can put these 3 together because they're all different color. I can put these 3 together because they're all different color. The last 2 I have left are these 2, which are different. So it's telling me that my last card also has to be different. So in this case, it would have to be green. And we'll do the last 2 attributes here, and we'll see that we do get the correct answer. So here we can look at the filling. So again, empty, filled, or striped. So I can put together things that are all different or things that are all the same. So that top row has filled, empty, striped. So those can make a set together just thinking of that attribute. The same thing will be true for the second row. And so this last row will have to make a set just within that characteristic. So what would the filling be here? It's going to be completely filled in. And then the last part is going to be the shape. So I'll group together things that are the same, all 3 same, or all 3 different. So I can put these together, and really I have lots of options. The options that I'm making here are not unique, and it'll still give me the same answer back. In terms of shape, I can have these 2 here, all different, and what I have left. So my last one would have to be. So this is telling me if we have not made any mistakes in the game, and I was careful about how I chose what my attributes had to be here, if I didn't make any mistakes there either, I should have a 2 green filled oval. And this is more fun when it's an actual game, right? But that is the answer that we get here. So if you were to play the game and you got all the way to the end and you had 1 card left, you can not flip it over, determine what it is exactly by looking at 1 attribute or 1 characteristic at a time. And possibly there's going to be a set containing that card. That's usually harder to do because you have to visualize it in your head before flipping it over. So that could be another variation of the game that you can do, where you try to find a set with that last card that's remaining, although it's not guaranteed that you will have a set here. And if you end up with 9 at the very end, again, you're not guaranteed to have any. You're only guaranteed when you have 21 cards showing up here. Okay. There was one other thing I wanted to talk about, but we definitely are out of time. So I'm gonna call it here. And if you guys want, you can deal out some cards and try to decide what sets are showing up. And maybe I'll stick around for a few minutes to do that. But thank you.
Before we do that, I think it's a great idea. Do we have any questions for Dr.
Yeah.
What did you learn from this?
I learned it in grad school. So anytime we did not want to be doing our research, we'd all come into like the lounge and work together and try to do it. And we came up with a lot of different variations because there were so many people that hadn't played it and then so many people that had played it a lot. And so we did things like in teams. So if Patrick and I were in a team and I saw a set, I would put a finger on one of the cards and he could try to figure out what set I was thinking of. He could have found a different one, but it has to include the card that I was pointing at. So some variations to like help people kind of learn a little bit more, or put them in groups with people who haven't played as much, or people that were really good at it. We'd make them have to find at least 2 or 3 sets already on the board before they were allowed to pick one up. Because some people who are really good will see it like in a split second. Before you're even done putting the cards down, they can see a set of 3 there that form a set. But it is a little bit addicting once you actually figure out how to play it and you can figure out the patterns there. Yeah. Is there a question in the back?
I was gonna ask where you came across this game.
Oh, yeah. Yeah, another math friend showed me it and then got our cohort kind of obsessed with it. Yeah. Any other questions?
I like how you were able to like turn into vectors,
Yeah.
because I feel like you could see it way better that way.
I feel like it's easier to prove things with the vectors,
Yeah.
but it's not easy for me to see a card and think oh, it's this vector. And so I know if I put these three together, it'll sum up to 0. But I feel like proof-wise, to actually explain things, it makes way more sense vector-wise.
Yeah, but like, let's say you have the cards that just set the vector on it.
Oh, yes. If the card had the vector on it, I think maybe it would be easier, but I'm not actually sure. You'd have to be doing a lot of modular arithmetic on all your components. Maybe seeing them vertically would make it easier too. Yeah.
Because you could have a set of cards.
Yeah. Yeah. I think that takes away a little bit of the fun though.
Yeah.
It just makes it a math problem.
I wonder, like, has anybody looked at doing this in like 4 dimensions?
Yes, I think they bumped it up 1 dimension. So I think maybe they stuck with 4 characteristics, but 4 attributes. And then some people also did 5 characteristics, but maybe the same 3 attributes within those. So there's plenty of variations that you can make there. But things that you'll probably have to change is a number of cards that you'll want to show up in your set so that you can do like the same type of arithmetic here. But the number of cards is linked to the number of attributes, right? That's going to be important there. But there's different ways that you can define a set. You can say 2 of the cards are the same. If there's 4 total for a set, 2 of the cards are the same and then 2 are different, or all same, all different. That could be a variation that you can do there that I think works and is actually already out as a game. I think maybe it's called quads. Yeah. But I'm not well versed in that one. I refuse to play when my friends would play it. So yeah. Any other questions? And I'm happy to kind of deal out some cards and try to look for some sets together. It might take a little bit of time at the beginning, but I'm also happy to give hints. If I see a set with a red diamond or something, I can give part of the attribute showing up there. But if you guys are interested, we can deal some out at the front here. Yep, no problem.
Before anyone sneaks out too.